For example number 6 out of our textbook, example number 6 wants us to restrict the domain of sine. And so I guess what we need to do is first we need to kind of remember what the domain for sine is and then the reasons why we would restrict it. So we need to graph the function y equals sine of x, and we're going to let our domain be trapped between negative pi over 2 and pi over 2. And so the reason that we're doing this is we're going to start to look at the inverse functions of the trig functions. And so, as you may recall, if I have an xy plane, I'm going to very lightly, with a very light color highlighter, draw what sine normally looks like. So sine normally starts at the origin, and it comes through and completes one cycle from 0 to 2 pi, because it has a period of 2 pi. And so what we have here is, right here is 2 pi, and it has it intercepts x at pi and negative pi, and then at negative 2 pi. So this is just regular sine of x, this right here, y equals sine of x. And so when we want to look at the inverse function, remember we said that sine of x was a periodic or sinusogenous function. So it would fail basically the one-to-one function test. In other words, if I came through here and drew a horizontal line, it would cross multiple times. And I said, hey, don't worry about that, because what we can do in those scenarios is restrict the domain in such a way that it would be only one-to-one for our restriction. So what the textbook is telling us to do is focus on the area from pi over 2 to negative pi over 2. And so if I focus only on that portion of the sine function, from here to here, I get a nice little graph that looks like this. So let me put that in red so you can see it better. So my sine function goes from here to here. All right, and so that's going to have a range, as it's written, from 1 to negative 1. So if this is the domain, then my range would be from negative 1 to 1. Now if I wanted to find the inverse of that function, I just need to flip-flop the x and y's. And one way that will help me flip-flop the x and y's is I can write this as a parametric function. And so if I wanted to write this as a parametric function, it's not that difficult. What we found to work in the past is if I take x and I let that equal t, then y would become sine of t. Okay, and then you would, so just look at that and process that for a second. So then what would my t values be? Well, my t values would be the same as my x values, right? So it would be t would be bound between negative pi over 2, or and pi over 2. So now if I wanted to find the inverse of this function, okay, the inverse just flip-flops everything. So now for the inverse of this function, if I flip-flop some things around, the inverse of this function is going to just kind of have some different things. So the inverse of my function, where my domain, let's list some of these things. So the domain of this would be the range of the old one, right? Because we're flip-flopping the x and y around. So the domain would be negative 1 to 1, okay? And then my range would be from negative pi over 2 to pi over 2. So here we have the original function, and here we have the parametric functions. We're going to use those to find the inverse function. But remember, what we're doing is we're flip-flopping the x and y. That's what the inverse function does. Okay? It flip-flops the x and the y. So now if that's the case, what would my inverse function be? Well, the inverse function would actually be, and we'll put it together, but if we look at the parametric equations, it would be x is equal to sine of t, y is equal to t. And so again, we're flip-flopping the x and y around. So then, depending on how I want to write this function, if I want to write it as a function of time or a function of t, it gets a little more tricky because then I have to take the inverse, right? Well, the inverse function is actually going to be written as the Cartesian. Okay? And that kind of means the same thing. Okay? So that kind of means the same thing. Oh, I'm sorry, it's supposed to be written in terms of x. So we can represent the parametric equations on our graphing calculator with this notation: f of x is equal to sine inverse. So this -1 means inverse of x, not t. Okay? But what does this look like graphically? Well, graphically, the inverse is reflected across the origin. And so if I have a range from negative pi to pi, right, let's just draw out our graph. Here is my y, here is my x. So my range goes from pi over 2 to negative pi over 2. And then my domain is from -1 to +1. And how would I graph that? Well, you got to look at the lower and upper boundaries. So if I look at where does this cross? It's interesting to see how it looks, because really what I'm going to do is I'm going to flip-flop the x and y. So if I just if it were possible, I'd flip this and then I'd flip it over the other way. And so what we would end up with is we have the point here. What is this point here? This point here is -1 comma negative pi over 2. So over here I have to have the point comma negative pi over 2. Oh, I'm sorry, I wrote down the inverse version. This is negative pi over 2 comma -1, and so over here it would be -1 comma negative pi over 2. So what I'm doing is my upper and lower boundaries, we're just flip-flopping the x and y values, okay? And so up here I have this value here, which is actually pi over 2 comma +1, and that would be this point over here, which will be 1 comma pi over 2. And then it's going to go through the origin, so it would look like this. And that's the inverse. Okay? Are there any questions on that? So again, this is going to be sine of x, inverse sine of x. And in function notation, we have the -1 right there. Okay? So now what does that mean? Before we're done, what does that mean? Well, if I plug this in the calculator, or if I did this algebraically, which it's not very easy to do, but what I should get is if they are inverses. In other words, if f of x is equal to sine of x, and the inverse is the inverse, and we denote it like this, then f of f inverse should equal x. Likewise, f inverse of f of x should equal x. So what we should get is if I say f of f inverse, I should get sine of sine inverse of x. And since these two are actually inverses, the inverse undoes what the sine function does, and we are left with x. Okay? And that's how that works. And we use this a lot to solve. In fact, we teach you this probably as early as geometry to solve for angles. But now we're going to use this a little bit more algebraically in your calculus class.